Let's say you have defined this regression model in which you want to explain the y variable by an intercept and a slope times the x variable. So you gather some data and you have this fitted regression. And your question is, with this value, this is a value, a scalar, and just a number, right? And you have the null hypothesis of the true beta being, for example, 0, right? So the alternative hypothesis is the beta, the slope, not equal to 0, right? So your question is, what is the probability of getting a value more extreme than beta hat? So this is a two-sided test. So what is the probability of getting something more extreme than the acquired beta hat? Okay, for example, this is 0. This is the null hypothesis. And in this two-sided test, you have to find the probability in the tails, right? So the sum of these probabilities will be the sum or the probability that something more extreme than your beta hat is happening, right? Finding a beta hat more extreme. So in this case, you can calculate the t-stat, which is just the estimator minus the hypothesis value, divided by the standard error of the estimator, which gives you this distance measured in standard errors, right? So this t-stat is just this distance measured in standard errors. And by using symbols, we can use the beta hat, just plug in the value of the beta hat, we can plug in the value of the hypothesized value, the null hypothesis value, divided by the standard error of the beta hat. So for example, if our beta hat 1 equals 2.5, then the t value, or t-stat, and we, of course, we need the standard error of the beta hat, which is 1.25 standard errors or units. And the t-stat in this case, with the null hypothesis of beta 1 equals 0, then we get 2.5 minus 0 divided by 1.25, which is 2, right? So our t-stat is 2, and we would like to know what kind of probability do we have on random if the null hypothesis is correct and the standard error is correct. What is the probability of getting a result more extreme than this? Which leads us to the question, which distribution does the estimator actually have? It turns out that the beta, the estimator, is distributed by the student t distribution. Okay, so what does it look like? It actually looks like the normal distribution, but it has fatter tails. So you have to go further away from the mean to cover the same probability as you would with a normal distribution. What's special with the student's t-distribution is that if you have more data, then this student t-distribution, it actually converges to the normal distribution. So for example, if you have more than 300 degrees of freedom, then you might use the normal distribution. So what is the degrees of freedom? Well, it's the number of data points, minus k, which is the number of slopes in your regression, right? And minus 1. So how can we use the t-table? You see that given a certain degree of freedom, you can get the number of standard errors, the t-stat, which you have to go from the hypothesized value to get a certain probability. And if you have a one-sided test, you use this column. And if you have a two-sided test, you use this column. So let's use the two-sided test. So if you only have 1 degree of freedom, then you use this part of the table, right? This part of the table. And this t value shows you how far away from the center you have to go in order to cover a certain proportion of the distribution. So in this case, you have to go 3.078 standard errors away from the mean to cover 80% of the distribution, which means that in each tail you have 10%. So if you have 1 degree of freedom and your t value is 3.078, then you know that by random chance you're going to get 20% of the cases more extreme values than this 3.078. Okay? So, what if we have more than 1 degree of freedom? If you have a lot of data and not a very good or not a very large model, for example, you have more than 300 degrees of freedom, you can use this degree of freedom equals infinity. This part of the table is actually the normal part of the table, because when the t-distribution, the student's t-distribution, has infinite degrees of freedom, then it's corresponding to the normal distribution. And you see that in this case, if you go 1.96 standard errors away from the mean or the hypothesized value, then you cover 0.95, which is 95% of the distribution, which means that a result more extreme than 1.96 would only happen in 5% of the cases. Remember that with a two-sided test, you count both the extreme cases on the upside and the downside. So what you say is that a result larger in absolute value than 1.96 standard errors will occur in only 5% of the cases. But what of the case when you have, for example, 80 degrees of freedom or 90 degrees of freedom? 90 is closer to this table than to this table, right? But in order to get a conservative estimate, you always round downwards. Not the case when you choose to use the df equals infinity, but in every other case you round downwards, because then you get a more conservative estimate. But in our case, our t-value equals 2, which means that we get something between these two t-values, these two critical t-values. So if we use the two-sided test, and remember that the tail distributions equals 1 minus the central distribution, right? So the probability in the tails equals, for example, in this case, 0 or 1 minus 0.8 equals 0.2, which is 20%, right? And in our case, we have the t-value equals 2, then we know that our value is somewhere here, right? So if we just point this to the letter 2 or the number 2, then what is the probability in the tails? We know that if we go 1.96, let's say this is 1.96, then we would cover 5%, or we would have 5% in the tails. And if we go 2.326, so we say this is 2.326, then we have 1 minus 9.8, we have 2%. So if we go this far out, we have 2% in the tails. So our p-value, the probability of getting something more extreme than 2 standard errors away from the mean, is between 5% and 2%.